points, almost like a shortcut across the entire universe. Such a classic sci-fi idea, isn't it? But what does cutting-edge physics actually say about it? Today, we're taking a deep dive into the, well, pretty mind-bending concept of wormholes. We've got a stack of really fascinating sources here that honestly completely reframe these cosmic tunnels, everything from Einstein's original ideas right up to the latest quantum theories. So our mission for you, the learner, is to unpack the reality behind the myth. We'll extract the most important nuggets and hopefully give you a shortcut to understanding one of the universe's most intriguing possibilities. Get ready for some serious mind melds and aha moments. Okay, to begin, let's explore the very fabric of reality itself, specifically how Albert Einstein just completely revolutionized our understanding of gravity. This is all codified in what we call the Einstein Field Equations, or EFE.
Right. It was a profound paradigm shift that Einstein kicked off, back in the early 20th century.
Hmm.
He basically reframed the whole universe. Gravity isn't some force acting within a static space and time. Instead, space and time are dynamic participants. Their actual geometry is dictated by matter and energy.
Okay, to make that maybe a bit clearer, think about Einstein's principle of equivalence. Remember that. The effects of gravity are locally indistinguishable from the effects of acceleration. So if you're in a windowless rocket that's accelerating, the force pushing you to the floor feels exactly identical to gravity here on Earth.
And that leads directly to the central idea of general relativity. Gravity is really a manifestation of space-time's own curvature, its intrinsic curvature. The distribution of matter and energy dictates how space-time geometry looks, and that geometry dictates how matter and energy move. The physicist John Archibald Wheeler had that famous summary: matter tells space-time how to curve, and curved space-time tells matter how to move.
Yeah, the common analogy is like a heavy bowling ball on a stretched rubber sheet, right? Creates a depression that a marble follows. But while that's great visually, it completely misses the time dimension, which you just mentioned is absolutely crucial. How do we even start to visualize that kind of curvature?
That's exactly the critical limitation of the rubber sheet analogy. You nailed it. In reality, general relativity describes the curvature of, well, four-dimensional space-time. And for many phenomena we're familiar with, the curvature of the time dimension is actually the dominant effect. We call this gravitational time dilation. Clocks in stronger gravitational fields literally run slower. And this temporal aspect is just fundamental for understanding extreme things like black holes and wormholes.
Ah, okay. So a key insight here is that the relationship between matter and curvature isn't really cause and effect one after the other. It's more like an identity. Space-time curvature is gravity. And this is all described mathematically by those Einstein Field Equations you mentioned earlier.
Precisely. Conceptually, you can think of the left side of the EFE describing the space-time geometry, the curvature part. And the right side, that's the stress-energy tensor. It describes all forms of matter and energy. So that's not just mass. It includes light, momentum density, pressure, even internal stresses. And this richness is essential because certain properties, like negative pressure, become really key later on when we talk about stabilizing hypothetical wormholes.
Right, so it's not just about mass, but everything with energy bends space-time. And that tiny mention of negative pressure, that's our first clue about how we might maybe defy gravity's usual rules, isn't it? That's quite a detail to keep in mind.
Absolutely. It's crucial. So in this curved spacetime, objects that are free from non-gravitational forces, they follow paths called geodesics. These are effectively the straightest possible lines through spacetime. But, this brings up a common confusion for a lot of people. If an apple is just sitting there stationary, why does it fall? It's not moving in space, initially anyway.
Yeah, that's a classic head-scratcher. How does general relativity explain that?
The answer is hidden in its motion through the fourth dimension, time. An object that seems stationary in space is still hurtling through time. All objects move through spacetime with a total 4 velocity, equal to the speed of light. For a stationary object like our apple, this velocity is entirely along the time axis. But in a gravitational field, that time axis is kind of tilted, like that. So when the apple is released, it just continues following its geodesic path. And because the straightest travel through time now points slightly towards the Earth's center in spatial terms, well, the apple begins to accelerate downwards in space.
And here's where gravity gets really counterintuitive, isn't it? In weak fields, like Earth's, what we feel as gravity is overwhelmingly because of the curvature of time, not really the curvature of space. Our weight is basically just the force needed to stop us from following our natural geodesic path through that warp time. This focus on time curvature is so critical when we start thinking about the extreme warping needed for something like A wormhole. It totally changes how you think about just, standing still. Okay, so with that foundation, understanding space-time as this dynamic fabric, we can now turn to the very first scientific attempt to actually fold it, the Einstein-Rosen bridge. It gets romanticized a lot as a cosmic shortcut, but its real origin was much more, well, down to earth.
Almost. Yeah, definitely. In 1935, Einstein and Nathan Rosen published this paper, The Particle Problem in the General Theory of Relativity. Their goal wasn't space travel at all. They were trying to address the problem of singularities in physics, where particles were modeled as points, which led to infinite field strengths, a real headache. They wanted a field theory where particles were finite features of the field itself.
And their solution was pretty ingenious, right? They took the Schwarzschild solution, that's the one describing space-time around a spherical mass, like a black hole, and they did this mathematical transformation, and the
Yeah.
result, a model where physical space was basically two identical flat sheets connected by a kind of bridge or throat.
Exactly. This construct, the Einstein-Rosen bridge, or ER bridge, that was the first formal description of what we now call a wormhole. But its purpose was to provide a singularity-free, purely geometric model of an elementary particle. So yeah, the ER bridge came from wanting to unify matter and geometry, not from dreaming of warp speed.
Okay, so Einstein basically opened the door conceptually, but what were the immediate, practical problems? Why wasn't this original ER bridge useful for, zipping across the galaxy in a sci-fi movie?
Well, the biggest problem, the killer really, was its catastrophic instability. It wasn't until 1962 that John Wheeler and Robert Fuller actually showed that the throat collapses incredibly quickly, so fast that not even light can get through from one side to the other. An observer trying to cross it would just be destroyed by a singularity before they ever got through.
Ouch, that sounds fundamental. Why is it so inherently unstable? What makes it collapse like that?
It's baked into classical general relativity. Gravity, at least for all the matter and energy we know classically, is attractive. It pulls things together. But a wormhole throat needs space-time to kind of flare out to stay open. And that's inherently unstable against gravity's tendency to collapse everything inward. The original ER bridge is a vacuum solution. There's nothing in it to counteract gravity's pull, so its collapse is swift and unavoidable. Which, yeah, makes it completely non-traversable, totally useless for transport or even sending a signal.
That's a really stark contrast to how we usually picture them, isn't it? So what would it take then? What's needed for a wormhole to actually be traversable?
That's exactly the question Michael Morris and Kip Thorne tackled back in 1988. Their analysis showed that to keep a wormhole throat open and stable, you'd need to thread it with some kind of substance with really extraordinary properties, something that violates what physicists call the null energy condition, or NEC. Basically, this stuff would need a large negative pressure. It would have to act like anti-gravity, pushing space-time apart to prop the throat open.
Negative pressure, anti-gravity. That sounds almost like, well, magic stuff. Does physics actually allow for this kind of exotic matter to even exist?
Well, here's the thing. While we've never observed macroscopic amounts of anything like it, quantum field theory does technically permit localized violations of the NEC. The Casimir effect is one example. You can get a negative energy density between two closely spaced plates in a vacuum. However, the theoretical constraint suggests that creating and sustaining a macroscopic traversable wormhole would need just an immense amount of this negative energy, or maybe incredible fine-tuning. It just seems highly, highly improbable. Think of it like needing an infinitely strong spring just to hold open a structure that gravity desperately wants to crush.
So the classical ER bridge snaps shut instantly. The traversable one needs basically impossible matter. This contrast really shows that any kind of persistent folding of spacetime has to somehow overcome gravity's fundamental tendency to just pinch those structures closed. The universe seems to like its rules, doesn't care much for our sci-fi shortcuts. Okay, let's talk about that phrase, spacetime folding over upon itself. It's super evocative, creates a great mental picture, but how do physicists translate that visual metaphor into something more precise without needing, cosmic origami skills?
Yeah, it's important here to distinguish between geometry and topology. They sound similar, but are quite different. Geometry deals with properties like distances, angles, curvature, how we measure things locally. Topology, on the other hand, deals with more fundamental properties of connectivity and overall shape. Things preserved if you stretch or bend the space, but not if you tear it. A wormhole fundamentally changes spacetime's topology. It introduces a kind of handle connecting regions that were previously separate.
Ah, okay. So the folding is just a way to visualize this topological change, like folding a piece of paper through a higher dimension to make 2 points touch. But it's not a literal physical process happening in some external higher dimensional space. Is that right?
Exactly. That's a really important point. General relativity describes space-time intrinsically, from within. It doesn't need some external bulk space for it to fold into.
Yeah.
When we say 2 points are close via a wormhole, that closeness is measured through the short path through the wormhole's throat, not through some shortcut in an imaginary higher dimension. The fold is just a conceptual aid, a mental picture, not a physical event.
Got it. Now, our sources mention something about two interconnected units of spacetime that could potentially interact, even if they weren't traversable. Is any kind of interaction possible across a non-traversable bridge, like the classical ER bridge? Even just a fleeting one-way glimpse?
Theoretically, yes, according to the maximally extended Schwarzschild solution. It's a mathematical model, mind you. It describes a space-time geometry with four distinct regions, including two separate exterior universes, or asymptotically flat regions. In this picture, an observer falling into the black hole from, say, Universe 1 could, in principle, receive light signals originating from Universe 2 just before, well, before they hit the singularity and are destroyed.
So it was a theoretical possibility of connection, a sort of fleeting one-way peek into another universe via the black hole interior, but totally useless for travel or sending messages back. It proved the connection was maybe possible in the math, but with fatal limitations.
Precisely. Information can cross the event horizon going inward, and an observer inside could briefly witness events from both asymptotic regions, both universes, but nothing gets back out. And both observers are inexorably drawn towards destruction at the singularity. So yes, it's a limited, doomed kind of causal contact. It's the most that classical general relativity permits for a non-traversable ER bridge. Falls way short of any kind of persistent interactive connection people imagine.
Right, so it seems classical physics really hit a wall with wormholes. They either need impossible stuff to stay open, or they just collapse instantly. Where did the story go from there? Because this is where it gets really fascinating, right? Einstein's other huge idea comes into play.
Exactly. In the very same year, 1935, that Einstein and Rosen published their paper on spacetime bridges. Einstein, along with Podolsky and Rosen, published another landmark paper. This one was on what we now call the EPR paradox.
Right.
It highlighted this really bizarre feature of quantum mechanics, entanglement.
Ah, entanglement. That's where two or more particles become linked, their fates intertwine no matter how far apart they are. You measure one, say, spin up, and the other instantly becomes spin down, even if it's light years away. Einstein famously called it spooky action at a distance.
And for decades, these two ideas from 1935, the ER bridge from general relativity and the EPR paradox from quantum mechanics, they were seen as completely separate things. Interesting curiosities in their own fields, but unrelated. But then, in 2013, physicists Juan Maldacena and Leonard Susskind proposed this absolutely stunning connection, the ER equals EPR conjecture.
Wait, hold on. ER equals EPR. So the geometry of the universe, the actual fabric of spacetime described by Einstein-Rosen bridges, might be the same thing as the spooky quantum connection of entanglement.
Wow.
Wow, that's not just a theory tweak. That feels like a complete redefinition of reality. Tell me more about how that connection works.
It's a profound idea. The ER-EPR conjecture posits that an Einstein-Rosen bridge is geometrically equivalent, or you could say dual, to an Einstein-Podolsky-Rosen entangled pair of particles. Essentially, the geometric connection through a wormhole and the quantum informational connection through entanglement are potentially two different descriptions of the exact same underlying physical reality. So when two black holes become entangled, the conjecture suggests they are connected by a non-traversable wormhole. And conversely, the microscopic connection between any two entangled particles could be viewed as a minuscule Planck-scale wormhole.
That is a direct and incredibly profound answer to that original idea of interconnected units of spacetime. The folding of spacetime, in this view, is the geometric manifestation of quantum correlation. And the historical irony is just incredible, isn't it? Einstein, who disliked the non-locality of quantum mechanics, co-authored two papers in the same year that, according to this modern view, describe two sides of the very same non-local coin. Amazing.
It really is. And this wasn't just, idle speculation. It was proposed as a potential resolution to a serious problem in black hole physics called the firewall paradox. That paradox arises partly from the monogamy of entanglement, a quantum rule stating a system can't be maximally entangled with two other systems simultaneously. ER-EPR offers a way out. It suggests the interior of a black hole is connected via these non-traversable wormholes to the Hawking radiation it emits over time. This could potentially keep the event horizon smooth, avoiding the firewall, which is a nice feature.
Okay, so if ER-EPR still implies these wormholes are non-traversable, does that mean our sci-fi dreams of using them for travel are still dead? Or is there a different kind of usefulness or implication here?
Well, yes, the non-traversability is crucial. But it's not a flaw in this picture. It's actually a feature. It ensures consistency with other fundamental laws of physics we trust, specifically the no-signaling principle. This states that entanglement, however spooky, cannot be used to send information faster than light. The non-traversable nature of the ER-EPR wormhole is essentially the geometric counterpart to that principle. If you tried to send a message by jumping into one end, you'd hit the singularity, you'd never emerge out the other side. So causality is preserved. The quantum shortcut can't be exploited for travel or faster-than-light communication. It means these wormholes are fundamentally about connection, maybe information, but not transportation.
That's a huge conceptual shift. Okay, so if ER-EPR is correct, the implications go way beyond just explaining wormholes. It suggests a whole new paradigm for what reality is at its most fundamental level.
Absolutely. The core idea is this duality between geometry and quantum information. And that leads to the pretty radical conclusion that spacetime itself might not be fundamental. Instead, the smooth, continuous fabric of spacetime that we perceive could actually be an emergent property, a kind of macroscopic illusion created by this incredibly intricate network of quantum entanglements between microscopic degrees of freedom.
Wow. So the very stage, the arena where everything happens, might itself be built from these quantum connections. That sounds a lot like the holographic principle, doesn't it? Where a 3D reality is somehow encoded on a 2D boundary surface?
It's definitely related and seen as a powerful extension of those ideas. The add-SCFT correspondence, for instance, is a specific mathematical example, a kind of dictionary that equates a theory of gravity in a certain volume of spacetime, the bulk, with a non-gravitational quantum field theory living on its boundary. ER-EPR takes this concept further. It suggests the geometry of the bulk, including these connecting bridges or wormholes, is directly encoded in the entanglement structure of the quantum state on the boundary. So in this view, entanglement doesn't just happen in spacetime. Entanglement effectively creates spacetime.
That's genuinely mind-bending stuff. But hang on, does all entanglement create a wormhole then, or is it only specific kinds of entanglement?
Good question. No, not just any entanglement. The specific geometry of the resulting wormhole bridge seems tied to the precise structure and, importantly, the complexity of the quantum entanglement. That principle of monogamy of entanglement is key again. Simple entangled pairs, like the original EPR pairs, are monogamous. They're exclusively entangled with each other, and those seem to correspond to the smooth, classical-looking, albeit non-traversable wormholes. More complex entanglement, sometimes called polyamorous entanglement, like, say, GHZ states involving 3 or more particles simultaneously entangled. While those can't be described by a simple classical bridge, they might correspond to something much more complex, perhaps related to the idea of space-time foam at the Planck scale. And there's still puzzles, like the superposition puzzle. How can you have a quantum superposition of states, some with no wormholes and some with wormholes, that results in a final state with a definite wormhole? That's still an active area of research.
Okay, so it's complex. Are there other theories out there exploring similar ideas of quantum bridges, or is ER-EPR pretty much the main contender right now?
Oh, there are other ideas being explored, definitely. Direct sum quantum theory is one example. It suggests that quantum fields might actually exist across 2 distinct sheets of spacetime. And the connection between them isn't one big bridge, but maybe an infinite ensemble of discrete mathematical bridges connecting specific points, like antipodal points within a gravitational horizon. What's particularly intriguing about that specific model is that it makes some potentially testable predictions, like a specific kind of parity asymmetry in the cosmic microwave background radiation. And there's some preliminary data analysis that seems tentatively supportive, but it's very early days.
Right, okay. So this is all incredibly theoretical, deeply mathematical. How do we even begin to bridge the gap between this abstract quantum gravity stuff and actual observation? I mean, we can't exactly go looking for Planck scale tunnels with a microscope.
No, you're right. Direct observation of those tiny quantum wormholes is completely beyond our current or foreseeable technology. But if a large object like an astrophysical black hole is actually a nexus of these quantum connections, as ER-EPR might suggest, then maybe it could leave subtle, detectable clues on a larger scale.
Okay, so how could we tell the difference between, say, a regular black hole and a wormhole, even a non-traversable one, from way out here?
Well, both would cast a characteristic shadow, that dark region, against a bright background, which telescopes like the Event Horizon Telescope, EHT, have famously imaged. Now, if a wormhole were somehow traversable, and if it had something bright like stars or gas on the other side, then its shadow might look different. You might see additional faint rings of light or even bright images inside the main shadow silhouette. That's something impossible for a standard black hole with its event horizon. However, if the wormhole is non-traversable, as the ER-EPR picture suggests, then our shadow would likely look almost identical to a regular black hole shadow, making it extremely difficult to distinguish just by looking at the shadow alone.
Right. Okay, but what about those non-traversable ones then? Can we detect those at all? Maybe indirectly?
There's a particularly intriguing idea involving gravity itself, gravitational perturbations. If there's matter hanging around on the other side of a non-traversable wormhole, connecting, say, two regions of our universe, its gravitational field could still propagate through the wormhole throat, and that gravity could then influence the motion of objects on our side. So by precisely monitoring the orbits of stars very close to a supermassive black hole, like the star S2 orbiting Sagittarius A at the center of our galaxy, we might be able to detect tiny, subtle, anomalous accelerations, wiggles in its orbit that aren't explained by the visible matter we see. That could be a sign of gravity leaking through from the other side.
Now, that sounds like a potential smoking gun, but how reliable would that be? Could other things, maybe more boring things, cause similar wiggles?
And that's the crucial question for anyone trying to actually do this observation. It's really complicated. You see, the clearest, most unambiguous signatures seem to require traversable wormholes, which, as we've discussed, seem highly improbable based on needing exotic matter. And for the non-traversable ones, while these gravitational perturbations are theoretically possible, the signal is likely to be degenerate. That means it could also be explained by other, perhaps more mundane astrophysical phenomena, like maybe there are just some unseen brown dwarfs or smaller black holes nearby causing the perturbations, or maybe our theory of gravity itself needs slight modifications in strong fields. So it's a tough situation. The wormholes we might have the best chance of seeing indirectly are, ironically, the ones least likely to actually exist in a stable, traversable form.
So if the connection itself is fundamentally quantum, maybe the way to probe it also needs to be quantum. It almost feels like physics keeps inventing its own versions of impossible burgers, things that defy classical intuition, but might emerge from quantum weirdness.
That's exactly the direction thinking is heading. It's a really exciting shift. The future of observing these deep connections might not lie solely with bigger telescopes, but maybe with quantum computers. The ER-EPR conjecture actually provides a new way to think about quantum teleportation, a real phenomenon we can already demonstrate in physics labs. In the ER-EPR view, quantum teleportation effectively renders the underlying non-traversable ER bridge momentarily traversable for the quantum information being sent. Not for a person, not for matter, but for the quantum state itself.
Whoa. Okay, so instead of trying to jump into a wormhole, we could maybe interrogate it using quantum states. Send quantum information through the entanglement link. That's a fascinating twist.
Exactly. The idea is you could prepare a particle in a specific known quantum state. Then you let it interact with one end of an entangled system. Maybe it falls into a black hole, which is one end of the ER-EPR bridge. Then you carefully measure the altered quantum state of its entangled partner. Maybe that's the Hawking radiation emitted by the black hole much later, which ER-EPR connects to the interior via wormholes. By analyzing how the partner state changed, you could deduce information about the nature of the entanglement link itself. And since the entanglement dictates the wormhole's geometry, according to ER-EPR, this is equivalent to probing the wormhole indirectly. So the telescope for examining a black hole's internal geometry might not be made of mirrors and lenses, but could be a vast quantum computer, capable of capturing and processing the delicate quantum information encoded in the Hawking radiation emitted over potentially billions of years.
Wow. Okay, what a journey that was. We started off with basic sci-fi tropes, folding space, and we went to Einstein trying to solve a technical problem about particles, then the need for this bizarre exotic matter, and now we're landed on the idea that quantum entanglement itself might actually be creating space-time. It really feels like the universe is playing 4D chess with reality.
It does, doesn't it? And that intuitive idea, the initial metaphor of space-time folding over upon itself to create an interactive connection, it actually turns out to be a remarkably prescient description of this modern quantum paradigm. The fold, in this view, isn't a classical geometric bending event. It's the macroscopic manifestation of a deeper microscopic quantum reality, entanglement. And the interconnection isn't some tunnel you can physically traverse, but rather a quantum informational link that literally weaves the very fabric of space-time together.
So what's the really profound takeaway here for you, the learner? What does this all mean?
Well, it strongly suggests that space-time, this stage we thought was fundamental, might not be. It might be an emergent property derived from a more basic alphabet, the alphabet of quantum information and entanglement. The geometry of the entire cosmos, its distances, its curves, even its connections like wormholes, it all appears to potentially be a kind of holographic projection of the underlying entanglement patterns of its constituent quantum bits, its qubits. So maybe the folding of spacetime is really just the universe communicating with itself through quantum correlations. And the wormhole is simply the physical embodiment, the geometric expression of that quantum conversation. Definitely something to mull over until our next deep dive.